Welcome friends. We will continue the discussion from our previous class. We were discussing about the disinfection methods, and in the last class we had an elaborated discussion on the chlorination process. Now in this class we are going to talk about other disinfection methods, which we will be basically focusing on the ozone and UV disinfection, and then we will conclude with kind of a comparison of the different disinfection methods, the major disinfection methods of course. Okay. So what we are going to cover in this class is the UV and ozone disinfection, and what are their abilities, what are their mechanism, their advantages and disadvantages, and then we will compare these different disinfection methods based on their byproduct implications and the applicability and other advantages and disadvantages. So another, like apart from chlorination, the other method which is being used for the disinfection for drinking water systems is the ozone. Ozone is basically the strongest disinfectant and oxidant available in the drinking water treatment. It is a colorless gas but very unstable. Okay, it is very unstable. If you compare it with the chlorine, it is quite unstable, and especially at higher pH. It can react with itself and with OH ion in the water, which can produce the hydroxyl radicals, and which kind of act as a very strong, in fact stronger oxidant than the ozone itself. Okay. So ozone lead to enhanced disinfection with reduced and lesser toxic DBPs. The DBPs mainly includes aldehydes, ketones, carboxyl acids. So it does produce DBPs, but not like haloacetic acid or trihalomethanes. It generally produced aldehyde, ketones, carboxyl acid kinds of DBPs, which are far less toxic as opposed to the DBPs produced by the application of the chlorine. There are added advantages with the ozone system, that it is helpful in the removal of taste and odor. It can remove the organic and inorganic matters. It can remove the micropollutants such as pesticides and pharmaceuticals, etc. Okay. And it can also help in enhancing the flocculation, coagulation, detention process. So that is the reason many times ozone is provided before coagulation flocculation process, but again in that case also this acts as a just primary disinfectant, and we have to use as a secondary disinfectant after that. Okay. So ozone will remove the bacteria, viruses, it will remove the various inorganics like arsenic, iron, manganese kind of substances, and it will remove the various organics like micropollutant and other stuff. Okay. The issues are that it because of its unstable nature, okay, it needs to be kind of generated on site and used immediately, as the half life is very short, approximately just less than 30 minutes. Okay. So that is why it can be used as a primary disinfectant, and unlike chlorine, it cannot leave a residual that can go into the distribution system and ensure the post treatment safety. So that is one of the unique advantages of chlorine system, that they leave a residual in the system which ensures the future safety as well, whereas the ozone, or for that matter UV or ultrasonic ways of disinfection, they will disinfect very effectively, but the disinfection lasts only till they are in the contact. Okay. After that, if any regrowth occurs, or if any, which is like potential of regrowth is very little or almost negligible, but recontamination may occur, and if some recontamination occur, it is not going to help in any way. So for that we need a secondary disinfectant such as chlorine or chloramine. We can add to maintain a disinfectant residual within the distribution system. So we can go for primary disinfection with the ozone, and then use the chlorine compound for secondary disinfection. Okay. We use CT concept for design of the ozone doses. Okay. So if you see the CT value for deactivation of the viruses, so like this is the chlorine compounds, they have CT in the range of, like chlorine has for 2 log reduction 3, chloramine has 643, and chlorine dioxide has 4.2. For 4 log reduction it is in this range. Ozone has just 1. Okay. So 1 milligram per minute per liter dose is good enough to ensure 4 log reduction. Just 0.5 milligram per minute per liter is good enough to ensure almost 2 log reduction of the various viruses. For Giardia, which is say a difficult to remove compound, again okay, if you see the chlorine compounds, so for say 2 log reduction, the doses required are 69, 15 or 1230, very high doses, whereas ozone requirement is just around 1 milligram per minute per liter. So you can see that how effective it is in comparison to the chlorine compound. So that is why it can be used as a primary disinfectant, and if needed residual chlorine may be like produced by adding some chlorine compounds for the secondary disinfection purpose. Okay. The other attributes of the treatment process is how we apply it. Okay. So as we just discussed that ozone is generated on site by a ozone generator, and this ozone generator either uses kind of dry air. Now for purpose of producing dry air, we need air dryers, because the air that we get in the atmosphere might have the humidity. So we need either air dryer okay, or compressor, so that we can use dry air from the atmosphere, or we use dry air cylinder right away, or we use liquid oxygen. Liquid oxygen is rather preferred because it produces better quality of the ozone in terms of like the which is being produced will have a higher percent weight concentration of the ozone. So that is why it is in fact more preferred, liquid oxygen is more preferred over using just simple dry air. The solubility will depend on the temperature and its concentration in the feed gas. Okay. So whatever like feed gas we are providing, either we are providing liquid oxygen or we are providing dried air, and that will generate ozone, and what is the solubility of ozone at that particular temperature at which we are operating will kind of guide how much soluble it is. The ozone contractors are generally of two types. So we can have the say diffuse bubble contractor or inline injection system, okay, which is used for dissolving ozone in the water. The diffused bubble system may be of the counter current flow. Okay. Generally it is of counter current flow. Counter current means we will pass water from the top, and the ozone will be basically, because it is a gaseous element, so it will be moving up. So the direction of the flow is different. The water moves from top to bottom, the gas moves from bottom to top, or ozone moves from bottom to top. So that is called the counter current flow. So this is more common for drinking water treatment, as it kind of provides a better contact time. Okay. If needed, we can go for more than one chambers, and then we can have like ozone flow in the subsequent chamber as maybe counter current or co-current, where both are passing in the same direction. Water is also a flow and the ozone is also a flow. Or we may have a flow through system also, where we are not adding any ozone, we are just allowing the ozonated water to stay for some time, so that the contact period is enhanced. Okay. So we may have that kind of different chamber as well. One of the issues with ozone system, that because the efficiencies of the like ozonation process, whatever ozone we are generating and how much it is getting dissolved in the water, it may not be 100%, and then we may get exhaust gas which might contain ozone, and it can basically lead to the exposure risk of the ozone. So that is why proper safety must be taken care, and the ozone destructors which usually use heat or a combination of heat and catalyst may be used to reduce ozone, to kind of remove the ozone from the exhaust air which is coming out of these systems. If you see the ozone reaction in the water, so when ozone is added in the water, basically a complex chain of reaction results, and there are different radicals can be formed. Okay. The OH radical or hydroxyl radical is the one of the most reactive and most common, but if there are like many times H2O2 and those kind of things are also added alongside, so that more like strong oxidant can be formed at times. So, the hydroxyl radical is stronger than ozone itself. Okay. The higher pH facilitates the ozone decomposition. So, that is why the reaction at higher pH will increase the hydroxyl radical formation and it will be more effective at higher pH. Lower pH less than 7 slows down the decomposition of the ozone. So, that will have higher concentration of molecular ozone and lesser concentration of the hydroxyl radicals. So, the rate of ozone decomposition that way increases significantly due to OH formation, hydroxyl radical formation when pH is greater than 8, and ozone residuals are difficult to maintain at pH levels greater than 9. So, if you are having a pH greater than 9, then ozone will not remain in the water, all ozone will actually react and will form the hydroxyl radical. Okay. And these hydroxyl radical are, because of their very high reactivity, they can actually lead to different kind of oxidation reaction, including the disinfection process as well. Apart from this, there are other water quality parameters that also impact. Okay, since we are talking about pH, so alkalinity itself becomes very important. Okay, we must ensure that there is adequate alkalinity to pH control. pH is not falling rapidly. So, if alkalinity is higher, it will have better pH control. If turbidity, organic matter or inorganics like iron and manganese are present in the system, so they will increase ozone demand, similar to chlorine demand. Okay. So, like there is chlorine getting react to these compounds, we call that chlorine demand. So, similarly if these kind of agents are present, so ozone will basically oxidize them, and in the process some ozone will get consumed. So, that will basically cause to the ozone demand in the water. So, more of these compounds, higher is the ozone demand and more ozone we need to supply. So, the process like becomes more costly, and the disinfecting and oxidative properties are relatively independent of temperature though. Okay. However, as temperature increase, the solubility of the ozone in water will decrease. So, this is the effect of temperature. Ozone application is more popular in the European countries. There are over 1500 installation in various European countries, and this data is also not up to date. Okay, this is around say mid around 2014 or 15 data. So, there might be more number of installation that has come up. In US there was around similar time there was around 250 installations. Okay. So, far less as opposed to the European countries. European countries are by far the most popular user, or they use ozonation for the great extent, as it appears from the number of installation itself, but this process has not had similar acceptance elsewhere. The main reason is the higher installation and operational cost, and the fact that you need to have a secondary disinfectant in the system if you want to ensure the post safety. So, in developing countries where the health risks are high, they anyway prefer chlorine because of its ability to ensure the long lasting disinfection abilities by ensuring the chlorine residuals in the treated water. So, on advantage side, the ozone actually rapidly reacts with the bacteria, okay, and virus, protozoa over a wide pH range. It is a strong germicidal properties. Then chlorination, there is like apart from ozone, of course we are adding ozone. So, apart from ozone no other chemical is being added to the water, which is also a gas and can leave the system very short lived, and the amount is also low. It is also efficient for organic degradation and inorganic removal. It removes color, taste and odor as well. On the flip side, the cost is quite high. It requires lot of energy, it requires qualified professional for design and system maintenance. Okay. Some DBPs will still be formed, but of course lesser than that, and it has no residual present in the distribution system. That is one of the major demerits, because it does not lead to any residual protection. Okay. And it may cause potential fire hazard and toxicity associated with the ozone generation system. Okay. The other disinfectant is UV. So, disinfection with UV radiation is also getting more popular. Okay. The UV spectrum is generally higher in energy than the visible spectrum. Okay. So, visible spectrum has higher wavelength and low frequency as compared to the UV spectrum. UV spectrum that way have higher energy than the visible spectrum, but lower than the X-ray. Okay. X-rays have even higher energy than the UV spectrum. Okay. And they have further kind of lower wavelength and like higher frequency. So, because of higher energy, UV disinfectant in water that contains bacteria and viruses can be very effective. It kills the bacteria, it kills the virus, it is also effective against the protozoa like Giardia, Limbia and Cryptosporidium, etc. So, when UV light enters a microorganisms, its energy leads to the damage of microorganism cellular function. Okay, it will damage its cellular function, and this damage could be by sheer physical damage. It can basically include the strand breaks. The energy is absorbed by the DNA and it inhibits the cell replication. Okay. Now, if you see the electromagnetic spectrum, okay, it is generally if you see the spectrum curve for cell inactivation. So, this is the wavelength range which basically is good for cell inactivation. So, around 254 nanometer, or some references say around 264 nanometers in fact. Okay. So, around this range, around 254, in between somewhere this range 254 to 264 nanometer range, we see the peak here appearing, and if we put the exposure of UV light in this range, it can lead to very high degree of cell inactivation. If we are putting exposure in other light ranges, it is not that effective. Okay. So, the curve shows here that this could be the ideal range for inactivating the microbes. So, the lamps that are used for disinfection purpose, there are low pressure UV lamps which is generally made of mercury, and then medium pressure UV lamps again made of mercury are there. So, low pressure UV lamps target the wavelength at 254 or 264 or somewhere in between, where the efficiency is highest. Generally 254 is the target. Okay. So, the lamp have a wavelength of 254, and if you see, this is a low pressure UV lamp. So, it will lead a light at this wavelength which is having very good disinfection abilities. This is the germicidal effectiveness for E. coli for say. The medium pressure lamp have high intensity as opposed to the low pressure lamp which works at a low intensity. The medium pressure have high intensity and they work at a wavelength which is far more wider. So, generally they can work in a wavelength range, higher wavelength range. Okay, in these means we can get of different types. So, they may work in a higher wavelength range, and a cumulative effect of this is appeared, and the intensity is also very high. We may have pulsed UV lamp which is intermittent emission of the high intensity. So, instead of regular emission of the either low or high intensity intermittent pumps may lead to intermittent lamps may lead to the impulse emission. Okay. The disinfection abilities are also quite good. Okay. If you see the required UV dose for 4 log inactivation of the common waterborne pathogens. So, typical UV doses are in the range of 40 millijoule per centimeter square, and this is sufficient enough to take care of majority of the microorganisms. Okay. However, some couple of species may require high, so that is there. Okay. So, if you see, these are the bacterial pathogens all taken care of more or less, okay, apart from just one spores. This is the orange one are viral pathogens, again these are taken care of, some might still persist, and the protozoa like Cryptosporidium and Giardia cyst are very well taken care of. Okay. So, that way UV is considered very effective because it can basically consider the it can take care of the Giardia and Cryptosporidium kind of species which are difficult to remove from the simple chlorination systems. Okay. This is couple of examples of the UV disinfection systems. Okay. So, eventually process is simple, we need to just make the light exposed to the water, UV light exposed to the water, and as the energy or the light beam incident on the cell, it will disrupt that, it will be basically through physical damage or the process that we were discussing, it can lead to the like deactivation or inactivation of the microbial species. So, advantage side, UV disinfection is effective against inactivating most viruses, spores and cysts. It do not alter taste, odor, color, pH of water. It does not require addition of any chemical. Okay, even the like ozone or gas form chemical is also not required here. It does not impart any toxic byproduct to the water. So, that is another very important advantage. Okay, it does not produce the byproducts. Systems are compact and easy to install. On the disadvantage side, the low doses of UV may not like effectively inactivate some viruses, spores or cysts. So, we have to see like we may need adequate doses, and but that might make the system costly. Another risk in fact is that the organism can sometimes repair and reverse the destructive effect of the UV. So, whatever destructive effect that UV is causing on the organism, they can actually repair that, known through a repair mechanism, which is the photo reactivation, and this happens in the absence of light as and known as dark repair. So, through this dark repair process, there is a possibility of microorganism reactivating themselves. Okay. But again the evidences are very little for this. On the other hand, the turbidity and total suspended solids in the water can also render UV disinfection ineffectiveness. So, like if there are turbidity or total suspended solids present in the water, then UV disinfection might not that be very effective. Also, it is not a cost effective option. Okay. The requirement of the cost and energy is relatively higher as opposed to the chlorination. However, it may be actually competitive with chlorination if we consider the complete chlorination dechlorination process and like put a system which follows all fire codes and other things, then it may be actually come to the comparative to the chlorination process. Okay. The point that it is ineffective against the turbidity and total suspended solids, it is let us say because you see the UV or in fact the similar mechanism is adopted in the ultrasonic exposure as well. Okay, that is even less used. Ultrasonic exposure is not a method for disinfection which is very popular these days. Still like chlorine, UV and ozone are by far the most popular mechanism for the disinfection. UV is very effective in smaller treatment facilities. Okay. So, if you see like many of you might be having the purifiers in your households. Okay. So, the RO system and many other systems comes with a UV lamp for disinfection purpose. Okay. Or you might be seeing advertisement on the television. So, UV is that way is quite popular for a smaller system, and that helps in because there is no addition of the sort of chemical is needed, all right. And generally these systems have ultrafiltration or in some cases even RO treatment beforehand. So, water quality is reasonably good and just a little exposure of UV ensures safety from the pathogens or any sort of microbial contamination. So, they works well at a smaller system. At a larger system we need lot of lot of arrangements to ensure that the penetration of UV is covering the entire mass of the water. Okay. And moreover, as just we were discussing, if you are having the turbidity and suspended solids present in the water, so what happens that these microorganisms may, like if you have say UV lamp here and it is putting a light beam and it is striking to suspended particles and microorganism is behind this. So, in that case this microorganism may not get exposed to the UV light or may not actually the UV light cannot directly penetrate to the microorganism cell and disrupt that or physically damage that. So, if there are more turbidity and more suspended solids, so more such protection can be like there for microorganisms, and the efficiency of the disinfection would decrease substantially. So, that is one of the risk with the these kind of processes. Many times the combination of disinfectant is also recommended, but very rarely used. Okay. The people have shown that particularly the laboratory tests have shown that they have the synergistic benefits for using 2 or more disinfectant together. So, that overall inactivation can be higher than some of these 2 independent systems. Okay. For example, like the ozonation before UV treatment is shown that ozone can degrade natural organics, okay, which can cause the absorption of the UV light and thereby allowing UV dose to be more effective disinfectant. So, if let us say organic compounds are there which is absorbing UV light, you put a UV light and the UV light is getting absorbed by the organic compound, it is not actually fulfilling the purpose of disinfection. But if you provide ozonation beforehand, it can actually degrade or decompose those organic matters, so that UV also becomes much more effective. Then the similarly, like chlorine dioxide have also shown the synergistic effect when combined with the ozone or chlorine or chloramines. You see one such example, like this is the deactivation through UV disinfection for the different species. Now, this particular species requires if you see the UV dose requires huge amount of UV dose. So, if you want to remove this and this together, so you need to actually cover whole spectrum with the UV. Okay. Similarly, if you are putting chlorine, so chlorine is very effective in removing all these compounds at a less dose, but if you want to remove cryptosporidium, you need to add chlorine doses up to here or say up to here. Okay. So, then you are actually like you need to add this much amount of chlorine. On other hand, for complete removal, you need to add this much amount of say UV exposure, you need to ensure this much amount of UV exposure. If you are using this together, so which this particular species which needs a lot more energy for removal. So, only for removal of this species you may need to add this much of extra power in the UV, which can be very easily removed with the just disinfection, like with little dose of the chlorine. Okay. And whereas this particular thing which needs lot of chlorine for removal might get removed with a very less dose of the UV. So, instead of putting a instead of going for chlorination with this much amount, or instead of going for chlorination up till this much amount, or going for the UV exposure from here to here, it is advisable to use let us say UV light only from here to here. So, saving lot of energy from UV and chlorine dose only from here to here. So, saving lot of chlorine and achieving removal of all the target microorganisms. Okay. So, that way like we can see that combination of disinfectant may also end up giving the better results at times. Now, if you see the byproduct implication of the different disinfectant, what we have seen so far. So, chlorination again as we discussed is one of the most risky in terms of byproduct formation. It produces trihalomethanes, it produces the haloacetic acids which are carcinogenic. Okay. So, that risk is there, where chlorine is obtained from hypochlorite, chlorate or say bromate formation can also lead. So, these are like some of the challenges with the chlorination process. Chloramination process, no significant byproduct issues. Okay. Nitrate formation in distribution has been an indirect issue though, because in distribution nitrate formation may be there. There are some byproduct formation in chloramination as well, but far lesser. Ozone will lead to bromate formation in water with high concentration of bromide, which could be an issue. Chlorine dioxide, again dosage rate in kind of controls the formation of the many of the byproducts. Okay. But still some products are found, and UV does not produce any significant byproduct. If you see the advantages and limitation of these common disinfectant methods. So, we already have discussed that the chlorination have advantages, that well understood and relatively simple method, established technology, okay, produces residual chlorine, whereas limitation is there are byproducts, there are taste issues, and it might be ineffective against cryptosporidium. Chloramination, again it is less effective than even the chlorine. Okay. So, that is one of the issues, whereas on the advantage side the byproducts are far lesser, the taste and odor issues are generally less than that of the chlorine. Ozone is very strong oxidant, very effective disinfectant compared with the chlorine. It can remove a variety of other substances including the organic micropollutants, taste and odor creating compounds, or it can oxidize iron, manganese kind of substances, and then they can be removed. The flip side, it may lead to the bromate byproduct, okay, and it is an energy intensive process, cost intensive process, and it does not lead any residual in the aqueous system. Then chlorine dioxide is again more effective than chlorine, typically at higher pH, and has less taste and odor issues, less byproduct issues, whereas again it is a kind of flip side, it is costly, needs great technical expertise, and comes with a risk as well. And UV, as just we discussed, okay, is very effective, especially against the cryptosporidium and Giardia kind of compound. It does not lead to the any byproduct, okay, but again it is less effective for viruses than the chlorine, and it also does not lead any residual chlorine for distribution, and may be actually requiring higher amount of cost and energy for the installation purpose, and of course the operation purpose as well. So, for choice of the disinfectant, these are the common disinfectant. Let us say we can use chlorine gas in the form of hypochlorite, chlorine dioxide, chloramine, ozone, ultrawide, and based on like which produces trihalomethane. So, we can see based on our requirement, okay, whether we want to apply it to large utilities. So, large utilities, again you see that ultraviolet is not an option, as just we discussed, or ultrasonic or any such method are not an option. For small utilities, all may be applied, the operator's skill required, what kind of this thing, meeting the bacteria, meeting the Giardia, cryptosporidium and virus removal standards. So, how good they are, what is the impact of turbidity. So, all these are the questions which can guide on to the selection of the appropriate disinfectant. So, with this we conclude the class here. We have discussed about the disinfection processes. Now, we will move to the next part on the sludge management, and then subsequently we will be discussing the advanced water treatment systems in the remaining lectures of the week. So, thank you for joining. See you in the next class.